Saxon's Trig, Lesson 72, one side plus two other parts, and then the law of sines, beginning on page 450. So part A is basically some terminology or some information, and then in part B, they do an application of what they're talking about. So in part A, they stop and give you a touch of a Greek lesson, and they say that the Greek word gonia means angle, trigonon means three angles, and metron means measure. And if you put all of those together, you're getting trigonometry. Obviously, that's the book that we're studying currently. And so trigonometry is the study of the measure of triangles, and that's why the bulk of what we've been talking about this year has been based on triangles. Now, if you're talking about a right triangle, if you know the length of one side and the measure of two other parts, so every triangle, let me back it up. Every triangle obviously is made up of three sides and three different angles. And I said we're talking about a right triangle here. So if you know the length of one side and the measure of any two other parts, so let's say I know this side and I know an angle and then I know this side, you can solve for all of the other missing parts. If the triangle is a right triangle, all we need to know is the length of one side and either the measure of another angle or the length of a second side, and that's basically what I showed you there. And then it says, what if it's not a right triangle? If it's at any sort of a slant, so maybe an obtuse triangle, so that it looks like a part of it is slanted, that side is slanted, it's oblique, and any oblique triangle can be solved if one side and two other parts are known. So whether it's a right triangle or an oblique, the same thing works. If I know a side and two other parts, I can find the missing pieces. So now, how do we go about that? And that's where we move into part B, the law of sines. Now, we said before when we had congruent triangles that we set up proportions. And so the law of sines is based on the proportion. So if you can identify a side, little a, and then the side opposite that would be the capital A, the angle, you do the sine of that one. And let's label this side B, matches with the side B over the sine of B. So now you kind of are getting the feeling why we call this law of sines, because it's using sine in it. So the angle opposite that is B, and then to finish, obviously side C would be opposite angle C. And so the sides are all lowercase letters, the angles are all uppercase. And so any set of two of these we solve by cross multiplying. So this is law of sines, and I would definitely want it in my notes to use as reference. So now let's do example 1. Solve this triangle for all of its unknown parts. Take the time to get everything drawn out here. So this is 23 degrees, B, A, 10, 7, and X. Okay, so if I begin, I realize it's not a right triangle, but if I begin with the law of sines, I check to see, do I know an opposite set, a side and its opposite angle? And if I have that, I can use law of sines. If I don't have that, we're going to learn another rule, not in this lesson, but in a later lesson, law of cosines, which will help me when I don't have an opposite set. So I have a 10, but I don't know the A. I have an X, and I don't know the B. That's certainly not helpful. But I know a 7 and the 23. These are the opposites. Perfect, I can use law of sines. So we begin with 7 over the sine of 23 equals, and then the next one is going to be based on what I want to solve for. Now, I can't really do the B here because I also don't know the side. Two unknowns isn't going to be helpful, but I can do the A. So 10 over sine of A. So when I cross multiply that, we're going to do 10 multiplying with the sine of 23 degrees, and that's obviously going to be done on the calculator, equals 7 sine of A. So if I'm writing it out algebraically, this is how I write it. But what I do is I shortcut rather than writing it out, I just do it on my calculator as I go. So sine of 23 gets a decimal times 10, dividing by the 7, which is what you would do if you were writing it out, And then I have a decimal sitting on my calculator. This wants to know the degree. So will I use sine or will I use inverse sine to spit out the degree? Inverse sine. So then I second shift, however your calculator wants it, and hit the word sine. And that should spit out a degree of 33.93 degrees. Now, I have the picture of what they gave me. I can make an assumption based on what I'm looking at that this is an acute angle and that the 33.93 should fit in here and be nice. They stop and say that just doing inverse sine does not clarify whether it was in the all or the students quadrant, first or second. So if it's in this one, it is the straight up 33.93 degrees. However, if it is in the second quadrant, it's 33.93 degrees shy of the 180, which makes it 146.07 degrees. And they're saying that A could be either of these. Now I'm saying in my picture, this is clearly not obtuse. But just to verify, maybe I have two sets, even though they gave me a picture. I don't think they're trying to be tricky. This usually applies when they don't give me the first picture. They just say, hey, I have this information. Then I need to make sure that I have both sets of answers. But to get B, I would take the 33.93 plus the 23, and then every triangle is worth 180. So you would be doing 180 minus your 33.93 and minus your 23, and see how many degrees that gives you. And since I don't have my calculator, okay, so that one's 123.07 degrees. Oh, that does not look like a 7. Now, B, again, it does not look like an obtuse angle, but maybe it is. And if I do the other, I would be saying 180 minus the 146.07 and the original 23. Did they give me that one? Oh, still looking. Oh, I don't think they did. All right, I may have to actually manually do this one. So let me actually do addition. 0.07, I know I'm going to have 0.00 to line that up. 6, 7, 8, 9, 6, 1. Okay, subtracting, borrowing again. So 3, 9.01. So 10.93. Okay, so this feels more like, so yeah. To be closer to what this picture, this triangle looks like, I would be using this one. However, they're saying, oh, this would imply my C. Okay, so they're saying C would be 23 degrees in both. A can be either the 33.93 degrees, or A can be the 146.07, which means B here was the 123.07, or B here was the 10.93 degrees. Oh, forgot my degree here. So I do have two sets of potential angles because I can't clearly tell whether what's acute, what's obtuse, and so forth. So I probably will go with both sets of answers. Now, let's get back to solving for the last piece, which we have not touched for either one of them, which is x. So I can equal, oh, and now I'm going to have to use the b both ways. So if I'm using this one, then my x is sine of 123.07 degrees. And ignoring that, I'm going to do sine of 123.07 on the calculator, get a decimal, times 7. divide by, and again, you may have to jot the answer down, or your calculator may be able to handle the divide by sign of 23, and that will give you your x. So you'll have an x, and then over here you'll have an x. And that is telling me, with the 123.0, yeah, I want to make sure I pulled it right, 15.01. And then it says, we note that there is no ambiguity when the law of signs is used to solve for a missing side. So it's saying that you should get the same answer when you do x over sine of 146.07, no, sorry, 10.9, I knew it didn't sound right, 10.93, because I'm using the b. If you do sine of 10.93 times 7 divided by sine of 23, you should be getting that same 15.01, because the length of the side should not be shifting in order for it to work to be its triangle. All right, so very wordy. That seemed a little more complicated. Usually you don't have to do multiple things when they're teaching it to you brand new. So let's move on to example 2. Solve this triangle for its unknown parts. Okay, what'd they give us here? 23 degrees, 10, 7, x, b, and a. Now this one is very clear that a is meant to be obtuse and b is meant to be acute. So do we have an opposite set? 10 over a, nope, 7 over 23. Okay, so here we go again. 7 over sine of 23 equals, they're trying to show you what the other triangle looks like. All right, so which one am I solving for? 10 over sine of a. Then that's looking an awful lot like what I just had here. So you've got the same scenario happening, except that now I know for sure I want the 146.07. All right, so then now I said here in this one, this side isn't changing. This isn't going to be 15.01. My apologies. It is going to be the 3.4. Okay, so in this triangle, they were trying to say this set of answers works. In this triangle, this set of answers works. This is a much shorter side, as you can see in their picture. It's not quite as clear in mine why it should end up being 3.4. So at this point, you would be repeating everything we just did, and then you would be doing the x over the sine of the 10.93, and yeah, just checking that they got the same 10.93 in this example, and then that should be giving you the 3.4 that we found up here. All right, let me see if we can do example 3 without any kind of confusion. I feel like I might be confusing you on what is such a very simple concept to actually do. So 7m, k, 30, 50, and a. Okay, first thing I would do is actually not look for law of sines. I would solve for a, because I know 2 parts, 2 degrees in the triangle. So you're going to do a is 180 minus the 50 plus the 30. So that's 80, 180 minus 80. So a is 100 degrees. And now I look to see, do I have an opposite set? No, no, yes. Okay, so we're going to do 7 over sine of 30 equals, and let's solve for the m, doesn't matter which one I pick first, sine of its opposite, which is 50, and then on the calculator, sine of 50 times 7 divided by sine of 30 will spit out m, 10.72, and then the same to get the k, so k over sine of its opposite, which is 100. So I'm ignoring the 1 in the middle now. Sine of 100 times 7 divided by sine of 30 tells me what k is. K should equal 13.79. Hopefully that one felt like it was a lot simpler. I wish that they had reminded me so that I could have explained to you the difference in the pictures, but hopefully this has all basically clicked.